Hello, welcome back. We will pick up pretty much where we left off in implementing, ignoring a loud noise, implementing the 6502 microcode. Now, we were following, in case you're new here and don't want to go back to the original video, we were following a run in a simulation of the test program until it deviates from an authoritative run. So in this case, we fail after 725 cycles. This is the graph of the run. This is a simulation showing the internal state of the CPU during the run. And 725, if we go to line 726, we get the line that is failing, which means that essentially we haven't implemented this opcode yet. All right, let's look what this opcode is. So opcode 0E, a arithmetic shift left of absolute address. Opcodes are available in the datasheet for the CPU. We're looking for ASL, which is arithmetic shift left, opcode 0E, absolute addressing. So that's the setup. That's where we are. What does ASL do? Well, we have a list here. We're saying the bits 0 through 7 of the operand, of whatever it is we're working on, need to be shifted. So 0 goes into bit 0, 0 goes into bit 1, 1 goes into bit 2. That's the arithmetic shift left. And then bit 7 goes into the carry. So if we look at the condition codes, we can see that bit 7, that the negative flag gets whatever was put in bit 7. The 0 flag gets the condition of the register after the shift. And the carry gets whatever was in bit 7 before the shift. So negative gets bit 7 after the shift, and the carry gets bit 7 before the shift. Cool. Except what you will notice here is that this doesn't work on the accumulator like we're used to. What does this work on? Let's look at the test plan, shall we? So ASL from addressing, so we read the opcode from a 36A, and then we read 2 bytes. This is absolute addressing. We read 2 bytes of the address from 36B and 36C, so that creates the address 8510. And then we read from 8510, we read 56. And then we write 56 back into 8510, and then we write AC. What does that mean? If we open a calculator and try to make it not flicker again, and we look, we've loaded 5, 6. So you see the bit pattern is 01010110, and we shift it left by 1. So let's just add 2 zeros and manually shift it. So 10101100, we get AC. So AC is 56 shifted left by 1 bit. So that's what we need to do. And the point here to look out for is the fact that we read it from memory and write it back into memory. This style of commands are called read, modify, write. And that's what will be implemented now. Now, read, modify, write, so far everything we've done, the difference between the opcodes was mostly about the addressing mode. So if we look at the code we had so far, and we look at the case that defines the opcode, and then we look at the different load A instructions. So what we see is that the difference between the different opcodes is with the addressing modes, and then the opcode itself is typically just a single cycle, or at most 2 cycles. Now, read, modify, write commands do not follow this pattern. They're actually a little different, which is why I thought they might be interesting enough to implement them here. All right, so first order of business is define this here. So 0E is the opcode, and we want handle ADDR absolute. That's just normal absolute addressing. And then handle op ASL. So ASL alphabetically should be around here. And we want this condition, so we don't want to do anything in the opcode if this is an address cycle. So that's the framework, that's the end case. And one last thing is if this is an unidentified cycle, set it to invalid state. Right. Okay, so first cycle here is going to be the op1 cycle. And now we need to think back of the interface. The ADDR handler will call us, will switch over to the instruction cycles with the, if we look at the architecture, with the address bus latches holding the address that was decoded, and with the DL, the data latch, holding the data that was fetched from memory. So that's the state we're in. That's the state where we were called. Now, with that in mind, what we need to do, so we have already read the value. We've already had this cycle done. What we need to do now is do an ALU operation. Okay, ALU operations. So, what we want is, we only need one of the inputs. So let's look at the ALU implementation and find out which, because honestly, I don't remember. So we have if we are on a shift left, we are taking the A input, which is kind of unfortunate. We would rather take the B input. I don't think we're using SLS anywhere. Let's see. Yeah, let's change that to, are we using SRS? No, we're not. No, let's leave it as the A input. Okay, so the A input comes from here, so from the special bus. What we want to do is have the special bus get fed from the data latch, and that will take care of this. So DLSB, that's the way to feed that. So we want SB source to be CTL DLSB. So that pretty much takes care of inputting the correct value to A. And now we want the ALU operation to be the shift left. So that is called ALU op. And we want that to be SLS. And then, sorry, there's one more thing to handle. What you will notice with the operation is that we're using carry in for what we shift. So let's talk about what this is. Results is a 9-bit result. It's a 9-bit value. And what it contains here is the A input, which is 8-bit, concatenated to whatever the carry is saying. Now the carry, if we follow the design, okay, we copied the wrong one. Yep, we want to call that ASL. Synthesis, simulation, implement. No, we want the RTL analysis. Okay. If we open the design, we can see that the carry input to the ALU, so this is the ALU, this is the carry input, and the carry input is directly fed from the decoder output. So whatever we put in the control signals for the carry will literally be what gets shifted into the bit 0 of the result of the ALU. Now, since the opcode requires that we feed 0 into bit 0, what we need to do here is to say control signals CTL that's the CTL. We want the carry. Here we are, control signals, and we want I forgot. Let's check what's connected. Carry in, so let's look at the top, which is called this, and let's look at the ALU. ALU result async. That's the ALU unit, and we see that carry I is connected to the control signal I ADDC. So that's the one we want to put here. I ADDC will set to 0, and that will shift in a 0 to bit 0 of the result. So that's enough to create the ALU operation. But we also need to create a bus operation on the same cycle. And what we see this bus operation do is it writes back to the same address we read from the same value we read from. Kind of pointless. I'm hoping we'll have time to get to how more modern versions of the 6502 did it. But that's what it did. So we want to say bus valid bus rec valid is set to 1, and we want the write to be set to 1 as well, and we need the data bus to contain the correct value. So we want the DBSRC to also be DLDB. Kind of guessing, but yeah, that turned out correct. Now let's see what that actually does, because here's the thing. So we loaded the data bus with the data latch, and that will take care of the value we're writing. And we didn't do anything with the addresses, but the addresses were latched by the ADDR cycles with the correct address, and that address is still there until we latch a new value. The latch here is explicit. So that will write back to the same address the previous value. Let's run that and see if it even compiles. Seems to compile. So let's run the simulation. And if I'm correct, we should get to cycle 7 to, it will call it 7 to 8. It will actually be 7 to 9. And that's indeed what happened. So we successfully created write to 8510 of the value 56. So that cycle was correct. Next cycle. The next cycle needs to write the actual value. So we are in cycle COP2. The ALU result is AC, as it should be. And the ALU ACR, the carry out, should be 0. Again, I don't find it. ALU B source, ALU result async. We'll get it in a second. ALU ACR, okay. Is 0. So what we need to do is this. First of all, ALU result is, let's look at it here. So we have the ALU, here's the result, and that's the result async, and this is ALU result. And now we can place it on the address bus low, but we can also place it on the SB inputs. That's this line. So what we need to do is set the special bus to the ALU result. That's the next cycle, C op2. So we want the SB SRC to be ADDSB. That's the ALU result. And then we want the data bus to contain what the special bus contains. So that's SBSRC, and DBSRC is SBDB. So now we've loaded the ALU result on the data bus. And with that, there are two things we need to do. First, we need to write it to memory. So we just repeat this sequence. This is a valid bus request. It's a write. The data bus contains the correct value. The address is still latched, so everything's fine. So that takes care of writing the value to memory. The other aspect is that we also need to update the flags. Now the flags, so let's recap. We need to update the carry flag, the 0 flag, and the negative flag. The carry flag gets whatever the ALU outputted, so it needs ACR. So we want control signals CTL ACRC and set that to 1. That will update the carry. And then the negative flag just gets from DB7, from bit 7 of the data bus, which is correct because remember the data bus is showing the ALU result right now. So control signals DB7N is set to 1. And then we need the 0 flag. And the 0 flag gets from DBZ. So you see we have DB1 or DBZ. So we want DBZ to Z. And last but not least, we are done. We want to switch to the next instruction. So this should take care of arithmetic shift left. What I want you to notice is that immediately after we handle the actual opcode, we jump to a subroutine that is called flags dump. And that makes sure that we've updated the flags correctly. So as we move through the test program, it will make sure that the flags reflect what they should reflect. Let's run that. Okay, something's wrong. Yeah, I didn't recompile. Sorry. Okay, and we're up to cycle 770, which means we've done opcode 0e. Now we can very quickly do the other arithmetic shift left opcodes because they're fairly simple. Because we just copy this. We need it 1, 2, 3, 4. 3 times. I'm going to not include 0a at this point. I'll explain why in a second. So 1, 2, 3. And those are 1e for a plus x. So the addressing mode is absolute plus x. And then 0.6 for 0 page. And 1.6 for 0 page plus x. Let's just place them all in order. Yeah, I didn't update the opcodes. So 0 page is 0.6 and 0 page plus offset is 1.6. And now if I rerun the simulation, we should get a lot further. We did not. 772. We expected verification second failed. It did not perform a write. Absolute test plus x. Okay, let's very quickly test that, and I may actually leave it for another time. Absolute plus x. And what we have is this. Cycle 0 is the fetch of the instruction. 1 and 2. Okay. Let's look at the caveats of the okay. So this page says how many cycles each addressing mode takes. And what she says is very interesting. It says note number 1. So let's look at AX. It says it takes 4 cycles. But then it says if we cross a page boundary, add 1 cycle. Also, add 1 cycle for store A absolute X, regardless of boundary crossing. So that's what the data sheet says. But in actual practice, other opcodes besides store A absolute plus X require this extra cycle. So that's what we'll do here. So absolute plus X will get input unconditional extra cycle. And then on the condition that says we need to add another cycle, if we're saying if not ALU ACR delayed, or and not unconditional extra cycle. And now we need to go to every place that already uses this addressing mode and say, okay, for op ASL, we want it to be set to, we want the extra cycle unconditional, but for load A, we do not want the unconditional extra cycle. It's just a weirdness of the 6502. And now if we regenerate, we should pass that point. We did not. 85D0 received. Okay, I'm going to leave that. I think it's not as important right now as to what I want to show you now. And what I want to show you now is how we can make the same code, the same Verilog code, and the same microcode, more or less, apply to two different CPUs. So up until now, we've been handling, or we've been implementing a CPU called the MOS 6502. So let's recap the sequence of how we actually did that. We have a test program. I'll use a different color scheme here just so we can differentiate which project it is. So the implementation is dark blue, and the test harness is light blue. And here we have the test program. And this test program tries to go through all the different combinations of what the CPU can do. All the opcodes in all of their combinations. And then we need to translate that into a memory image, we can do with a compiler, that's not a problem. And then we need to translate that into an authoritative test plan, which is what I kept looking at all of this time. I have a bunch of needlessly open windows. Let me just close them a second. Okay, so this test plan that we kept looking at, and that the test harness in Vivado kept looking at, needs to be generated somehow. Now, the way I've been generating this so far is using a project, Visual 6502. This project. What this project does is it took a 6502, a MOS 6502, it stripped away the cover, took a photograph of the silicon, figured out where the transistors were and what they did, and then it runs a transistor simulation of the CPU. So you can actually now give it cycles. Let's go to the advanced view, slightly better. So you can give it cycles and you can see the internal state. And that's an authoritative execution. It's not executing on an actual CPU, it's executing on a simulation of the CPU, but it's a transistor level simulation. It is 100% accurate. Now, I'm not using this, which is a JavaScript implementation. I'm using a C++ implementation by the same author, but the concept is the same. So I go to this directory. It's called Perfect 6502, and then I type make, and it executes the code on the simulated CPU, and it produces the test plan. Now, and that's for the MOS 6502. But now I want to implement another 6502 variant. I want the Western Design Center variation. And I don't have a transistor level simulation of the CPU. I don't have an authoritative source, except the obvious one, which is 6502, right? I can take the actual chip and use that. So that's what I did. This is a 6502. I tried to do a live cam, but I couldn't figure it out. I had technical problems. So you're getting static image, I'm sorry. But 6502, just RAM, and all the buses are hooked up to an Arduino Mega, which is hooked up to my computer. And now the program on the Arduino, I can talk to it. And then I can ask, what's the CPU state? I can read memory. I can write to memory. So now if I read that same memory again, it will give me the new value. And I can cycle the CPU and see what it's doing. And it also gives me the signals it outputs. So if it's a sync or it's a vector pull, it tells me that that's what it's doing. And now it's executing code. So what I can do is I can take the test program I converted into a mem file of a memory image and write a Python program that will read that and dump it through the serial interface to the memory of the actual test setup, and then execute this program and record what it's doing. Now, it takes a while. I will actually show you how long it takes. So I need to run a gen test plan. And then I say the port, USB, and the test program will be test program Western Design Center. And we want to write it out to test plan wc.mem. And I'll do it like this with time to measure how long it takes. And it sets up, and then it starts writing the memory image to the RAM. And that takes a little while. And then it starts executing the code. Now, you may be wondering, how does it know that the code finished? And the answer is that the test program defines special memory areas. And so any write to address 200 will be considered the program finished. And there are other triggers that do stuff. So essentially, this is a computer. So the Python program that runs the program also looks at where things are written. And if they're written to certain addresses, does certain operations, which allows me to check the reset behavior. It allows me to check the interrupt behavior, etc. And so when it detects a write to 200, it will finish. Now, as you'll notice, it's been running for a while now. Total execution time is 1.5 minutes for this program, for 12,500 cycles. So you do the math. It's around 20 hertz, the effective CPU speed here. But thankfully, the Western Design Center CPU can go so low. But here we are, writing 200, and the program is done. And now we have a test plan for the Western Design Center. So let's copy that to the project. I actually copied it already. And set up a test harness or test bench for the Western Design Center. So if we look at the project under simulation sources, we have a directory called MOS. So that's the MOS variant. And if we look what it have at MOS top, you'll notice that it doesn't have much. It just instantiates a module called simulation top, and it gives it a bunch of parameters. Most importantly, CPU variant is 0. So what we need to do, we need to create a new directory, create simulation sources, we'll say a new one, which we'll call Western Design Center. And we'll create a file, which is system verilog, that will be called WDC top. And then we will want to add a bunch of files. So first of all, sources, sim, we want the simulation top we mentioned before. And we also want the mem files containing the test program and the test plan. So those are our references. And now we want to set this as the active test bench. We want to copy this line from the MOS version to the WDC top. And we want to make a couple of changes. First of all, the CPU variant will set to 2. And of course, the test program, we won't use MOS, we use WDC. And now if we run the test bench again, we'll be comparing the execution not to the MOS test plan, which was run on an authoritative MOS CPU, but to the Western Design Center test plan, which it was created on a Western Design Center CPU. So run simulation. And we fail already at cycle 52. Why do we fail at cycle 52? We expected the address 4102 and we got the address 41F4. Why? The reason is the difference between the CPUs. That's not the one I want. I want this one. So this is the MOS CPU. Let's open the test plan for Western Design Center. And we are in cycle, so we need line 53. So we want the branch plus instruction, the first branch plus instruction. Okay. So what you'll notice is that on the MOS, we read from 4101 the opcode, and we read from 4102 the relative offset to jump to. And then we do a dummy read for 4103. And then we read from 41F4, which is the incorrect address, because we needed to update the most significant byte. And then we read from actually 40F4. Now this read from 41F4 annoyed people because this address, this is the next program counter in line. It's okay. It's kind of expected. It's under control. This address is unrelated to anything the program actually needs. So that was considered a bug in the CPU. As a result, the 65C02 fixed that. So we read the opcode. We read the relative address. So far, so good. And then we read a dummy byte, a dummy address. We read a dummy address again. And then we read from the correct address. So what you'll notice is that here we read from just some random address. Here we read from the program counter again. We still need this cycle in order to calculate the address, but we're not issuing a spurious address while we do that. So let's implement. Okay, so we go to the branch. And what you'll notice is that the decoder gets the CPU variant. So in the decoder, we know the variant of the CPU we're currently implementing. So go to the branch, and here, okay, so ADDR1, we just read the relative byte. ADDR2, we perform the ALU operation to add the least significant byte. And then in ADDR3, if we don't need any further addresses, we just go to the next instruction. But if we do, okay, sorry. ADDR3, if we don't need to jump, we just carry on. And in ADDR4, we do the ALU of the address. And then in ADDR, sorry, I kind of lost track. Let's see the execution. That should tell us how we don't get the execution, because we did not create a graphic for it. So here we have the waveform, and here I'm gonna need to add sorry, let's okay, don't remember off the top of my head how to create a new waveform. I don't want to spend your time on it. So let's just again recap. ADDR1, we've just fetched the opcode. Now we're fetching. Now we are checking whether the we've fetched the opcode, and we fetch the operand, because we always do. But we check the condition, and if it's not met, we just move to the next instruction. So we're here. That means that we need to branch. So we're setting the ALU to add to the least significant byte, and we're outputting the program counters. So this is PPL cycle 1, cycle 2, cycle 3. This is cycle 3, which is this one, which we still do correctly. And then we look at the result of the ALU, and we check whether we need to cross a page boundary. And if we don't, we do new instruction. If we do, we're already doing ADDR out program counter. But the ADDR out program counter, what you'll notice is that we've already set the program counter to the new value. So this ADDR out program counter outputs to the incorrect value. However, in the previous instruction, we've already read from the program counter before the branch. So the latches will still have it. So all we need to do is say if CPU variant is smaller than 2, smaller than 1, okay, equals 0, then ADD out program counter, else a bus rec valid equals 1, and everything else is already set up because the latches already contain the program counter before we updated it. This should solve our problem. Let's see. Simulation. And we are at 61. Cycle 62. That's a jump. And the complaint, so yeah, that solved it for the MOS, for the Western Design Center. But what we now need to make sure is that we didn't break the MOS variant. So now we need to go back here and run the simulation again. And make sure we still run till the same point where we failed the last time. So we didn't introduce any regressions. Okay, so that was one. Now let's go back to the Western Design Center one. That's a bit annoying. And we were we need to regenerate like this. So we were in cycle 62. Cycle 62, branch always. Now the branch always, it's the same problem, but I think branch always was independently implemented. That's opcode 80. So opcode 80. Sorry, my bad. Branch always is a new command. It was not available on the Western Design on the MOS variant of the CPU, which means we did not implement it. So we need to implement it now because, well, okay. So here's the thing. We want to call handle op branch, so we don't have to re-implement it. But we only want to do that if we're in the correct CPU variant. We don't want to introduce this command if we're in the MOS version of the CPU. So what we want to do is, if CPU variant is greater than 0, only then, no, let's try and keep it compact, else, and by default we said invalid state. So that's what we'll do here as well. Set invalid state. Okay, on handle branch, so we have condition flag, and we defined condition flag here. So a condition flag looks at instruction registers 7 to 6, the 2 bits here. But we have a problem, because these 2 bits aren't enough to detect the branch always instruction. Branch always instruction, we were relying on the fact that if we look at here, branch plus, branch minus, branch overflow clear, branch overflow set. So all of these are at regular interval, but they're all on odd most significant nibble, and branch always is on an even. So we need instruction register. We need also instruction register bit number 4. Okay, so what we want to say is instruction register bit 4. If it is set, then we want to use that. Otherwise, we want a constant 1. So that means that if the instruction bit is 0, we always say the condition is true, and this will be a branch always. I'm trying to avoid making the design bigger. I'm not sure I'll succeed. We'll see. Let's run this again. Not particularly. Okay, so we were at 80, and we're asking if CPU variant is bigger than 0, then handle op branch. And because the condition here is like this. So what we want to do here, condition flag, we won't set it to 1. We set it to the opposite, to the inverse of instruction register 5. Which will cause this condition to always be true. No, I don't need that. The instruction register 5, I know what it's going to be, right? It will be at 0. So if it's going to be 80, bit 5 will be 0. No, that should have worked. Let's look at that again. Condition flag. The condition flags are those. And the condition flag is not the same as instruction register 5. However, condition flag, I set it to 1. And instruction register 5 was 0. And yet, I needed to set it to 0. We're always branching. The condition here says don't branch. I reversed the meaning. So we need to set it to 0. Sorry about that as well. But this way you know that it's authentic, that I'm actually writing the code right now and I'm not copying it from somewhere for what it's worth. And we got to cycle 282. So that was enough to get us all the way to instruction 282, which is push X, which is another new opcode that wasn't implemented before. So essentially, I think I covered everything I really wanted to show you. I wanted to show you, first of all, I wanted to show you the read, modify, write commands. They're not fundamentally different, but they're somewhat different. And then I wanted you to show you the ability to customize the design so that the same generic microcode implements two variants of the CPU that are different, have different opcodes, and the opcodes themselves sometimes behave differently. And we do that with the conditions with the CPU variant, which is a constant. You will notice that it's passed to the decoder not as an input, but as a parameter. And since it's a constant, Verilog, when it compiles this, it knows only to look at the relevant part. So the irrelevant part doesn't takes up logic in the final synthesized design. So those were the two parts I wanted to show you. And I think that's where we'll sign off for this series. Thanks everyone who joined. Probably next week won't have a live stream, but I will continue to live stream as soon as I find something that I think is interesting enough. And in the meantime, like, subscribe, Patreon, etc. Yada yada. Okay, thank you. Thank you for joining.